Some manufacturers have chosen to install air suspension in place of conventional springs in their passenger vehicle, not only providing ride quality, but also allowing for self-levelling and height adjustment. Air suspension systems can be categorised as self-levelling or active height adjusting when used in passenger vehicles. Although similar in appearance and function, they operate to achieve different outcomes. Self-levelling systems use air springs in place of conventional coil or leaf systems. The air springs are carefully designed rubber and fabric bellows containing compressed air, inflated to a certain pressure. The rubber bellows do not provide force or support load. The column of air does this when inflated. Traditionally, load levelling systems only require air springs on the rear of the vehicle, with conventional springs retained in the front. Although modern systems use air springs on all corners of the vehicle. If we look at when load is applied to the passenger cabin or to the rear of the vehicle in the form of a trailer, the rear ride height of the vehicle is dramatically reduced. In a conventional suspension system, this weight would preload the springs, changing their spring rate dramatically. With less ground clearance, increased spring rates and limited shock travel, passenger comfort is compromised. If we factor in the increase in front ride height, altered steering and suspension angles and changed headlight angles, passenger safety may also be negated. A vehicle fitted with an air-controlled load levelling system will retain its original ride height regardless of the load in the passenger compartment, maintaining a safer driving platform. How does it work? Well, in its simplest form, a load or height sensor attached between the rear axle or a movable suspension component and the vehicle body detects a change in measurement between the two components. As the linkages move, they act on a rotary position sensor. The output from this sensor is analog in form, so the signal from the sensor is always proportional to the change in vehicle height. The signal is sent to the control module where factors like vehicle speed, ignition position, and the height override switch position are taken into account. The signal is processed and the control module energises the air compressor control relay. At the same time, solenoid valves are opened, allowing compressed air into the bellows. As the air volume within the air chamber increases, the bellows expand, effectively raising the vehicle. The ride height of the vehicle is assessed by the control module using constant feedback from the position sensors. Once a predetermined height has been reached, the control module switches the compressor relay off and closes the inlet air solenoid valves. Another advantage of using air springs is that as the pressure in the bellows is altered in accordance with the load, the spring rate changes proportionally to the load. When the load is removed from the vehicle, the ride height is greater than necessary. Feedback from the position sensors is processed and the control module opens the bellows vent valve solenoid. Air is exhausted from the system until the optimal ride height is achieved. Be aware when using a hoist and raising vehicles fitted with self-levelling suspension. The control module will see the increase in ride height and begin to exhaust air from the bellows. This is not a problem when the vehicle is in the air, but as it's lowered to the ground, the bellows may distort and pinch, causing irreparable damage when the compressor engages and inflates the bellows once again. Always check the vehicle operating manual before raising or lowering on a hoist. Instructions on how to bypass or simply switch the system off will generally be supplied by the OEM. Active height adjusting air suspension systems not only incorporate load level control and user-defined ride height functions, but also communicate with the stability control platform to ensure a safe and comfortable ride, regardless of vehicle height and passenger compartment load. Apart from a more complex control and monitoring system, this type of suspension often uses load-dependent shock absorbers to complement the air springs. Each suspension strut is allocated individual control valving and a position sensor. This means each axle may be electronically controlled with load-dependent dampening. The dampening force of the struts can be varied according to air spring pressure, using an integrated control valve. A sensing diaphragm within the valve is connected to the bellows chamber and is controlled by the air pressure within. The air pressure acting on the diaphragm is always proportional to the load applied to the suspension. The diaphragm is attached to a control valve mounted between the shock's main and reserve working chambers. On rebound, the piston is drawn upwards in the main chamber. Some of the oil flows through the rebound valve, while the remainder flows through bore holes located in the upper section of the main working chamber to the lower side of the control valve. At this point, there is a very small load in the vehicle, so the air pressure within the bellows is also relatively low. This means there is very little pressure applied to the control valve diaphragm. The return spring will therefore keep the valve open, allowing fluid flow from the main chamber directly into the reserve chamber. Allowing the majority of fluid to bypass the rebound valve effectively reduces the shock's dampening force. As the air pressure within the bellows increases, due to increased passenger or towing loads, this higher air pressure acts on the dampening control valve's pressure diaphragm. The return spring's force is overcome and the control valve is closed. Fluid is no longer able to bypass the rebound valve, thereby increasing the shock's dampening. During the shock's compression stroke, the rebound piston is pushed downwards through the main chamber, forcing fluid through the compression valve into the reserve chamber. With a light load in the vehicle cabin, the air pressure within the bellows remains low. This low air pressure is applied to the control diaphragm. At this point, the valve's return spring force is greater than the air pressure acting on it, so the valve remains open. With the control valve in the open position, fluid is able to exit the reserve chamber via the upper chamber boreholes entering into the main chamber. This softens the dampening effect of the shock absorber. If the passenger compartment load is high, or the vehicle is towing, the air pressure within the spring bellows will also be high. Again, this pressure acts on the control valve diaphragm, closing the bypass port. All fluid within the shock must now pass through the compression valve into the reserve chamber. This has the effect of firming the dampening action under the compression stroke. The compressed air is produced by means of a single piston compressor with an integrated air dryer. The air dryer is used to prevent moisture contamination of the spring bellows and valving. The pressure accumulator is used as a storage cell for the compressed air. This allows for more rapid height changes or adjustments for load capacity. The air pressure sensor is a 3-wire analog output sensor, generally mounted in the accumulator. The produced signal is proportional to the pressure within the accumulator. Most ride height sensors use an inductive type design. These sensors are able to output 2 different signals with the same degree of movement. These are contactless sensors and as such are not subject to the same levels of wear and tear as older style resistive sensors. They operate using 2 sets of coils or windings known as the stator and rotor, formed into a printed circuit board and mounted in close proximity to each other. The stator is fixed to the sensor housing while the rotor can move with the input shaft. An AC voltage is induced into the stator through excitation of the rotor. The induced voltage will vary based on the angle of the input. At rest, with no angle change, an equal amount of alternating current flows through both windings. As the rotor changes angle, so does the amplitude of the stator winding phase angle. This signal is then conditioned and amplified via an integrated circuit for either digital or analog output. The sensor housing is mounted to the chassis with a linkage arm between the sensor pivot shaft and a suspension arm. As the vehicle body moves in relation to the suspension position, the linkage acts on the shaft, changing the measured suspension angle. In the most basic form, a self-levelling air suspension system acts to raise or lower just the rear of the vehicle, using minimal input signals. If the vehicle height sensor voltage has met a predetermined level and the ignition is on, the module energises the compressor control relay and the airbag lock-off valves. Airflow from the now running compressor is able to fill the airbags, raising the height of the vehicle to compensate for cabin load. Once the vehicle reaches a predetermined rise, acts on the shaft, changing the measured suspension angle. In the most basic form, a self-levelling air suspension system acts to raise or lower just the rear of the vehicle, using minimal input signals. If the vehicle height sensor voltage has met a predetermined level and the ignition is on, the module energises the compressor control relay and the airbag lock-off valves. Airflow from the now running compressor is able to fill the airbags, raising the height of the vehicle to compensate for cabin load. Once the vehicle reaches a predetermined ride height, as measured by the ride height sensor, the module disengages the compressor relay and closes the airbag lock-off valves, trapping a fixed quantity of air within the bellows. When the load is removed from the passenger compartment, the air within the bellows is able to expand, raising the height of the vehicle. This new height is signalled to the control module, whereby the bellows lock-off and discharge valves are opened and air is exhausted to the atmosphere. The bellows deflate, allowing the vehicle height to drop. Once the unloaded height has been reached, as monitored by the load sensor, the module closes the lock-off and discharge valves. The most advanced form of air suspension is the 4-channel type, whereby each individual air spring and shock can be monitored and controlled. These systems communicate with the engine control, stability, transmission, anti-lock braking and body control modules over a vehicle network. They allow the driver to raise or lower the ride height of the vehicle by simply pressing a button, or the suspension control module may be programmed to lower the ride height when parked for ease of passenger exit or entry. If a trailer is attached to the vehicle, the suspension control module will receive this data over the network from the trailer lighting module and enter a towing program. Headlamp height adjustments needed to compensate for body movement can be made faster using input data from the suspension control module. Likewise, the stability control platform can command vehicle height, suspension spring rate and shock dampening adjustments to allow for active vehicle dynamics and anti-lock braking functions. We can see that the airflow diagram for these systems is not that different to the basic single-channel type. The pressure accumulator is used to maintain a large supply of air for the bellows. Lock-off valves for all air springs and dampeners, including pressure relief, discharge valves, and compressor temperature and pressure sensors are also utilised. The ease of integration with other vehicle systems makes air suspension an attractive alternative to traditional types. Keep training, and thanks for watching.